Let's go. Okay, welcome everybody. I hope you had a really good summer. We are back in the and our first speaker is Stefan Rotter from Wien University, and he will be talking about transforming space with non-emission dielectrics. So whenever you're ready, go ahead, Stefan.
Okay, so thank you, Andreas and Francisco, for giving me the opportunity to present some new results here in this virtual seminar. I will speak about the problem that many people have been looking at already, which is the following problem, that when you shine a laser or any other wave on an object, then you'll get scattering. So and through this scattering, actually, you will see the object. And the question that many people have asked is there actually a way that you can prevent this scattering, such as to make this object invisible? And about 15 years ago, Ulf Leonhardt and John Pendry, they came up with a very interesting concept, showing that you can actually build a cloak around this object and thereby prevent the scattering and make this object invisible. What many people actually in the non-Hermitian community have been looking at is the opposite. Rather than building something around the object, non-Hermitian effects were used to actually guide a wave through an object. And of course, the magic ingredients that would make such a thing possible are gain and loss. So gain like from an active material that you find in a laser, or loss like in black paint that would absorb all light. I'm sure that many of you are familiar with the work on unidirectional invisibility that was published about, I would say, 10 years ago by Tsampikos Kotos, Dimitri Christodoulidis, and others. They showed actually that by stacking gain and loss components after one another, you could create a Bragg grading. And this Bragg grading, if you tune the parameters correctly, would actually let the light coming in from the left pass through as if this whole material wasn't there. But if it would come in from the other side, then it would scatter. So in this way, they created a unidirectional PT symmetric periodic structure. And this caused a lot of excitement. Many people were working on it. Also many people here in the audience. I list a few names here of people who contributed to this kind of research, showing that you can do this also with acoustic waves, that there are also nonlinear effects there, that you can create more complicated structures. Experiments were being performed in various domains. So much research has been carried out and also been reviewed in those reviews that I show here. Now, in the group in Vienna, we entered this field when we asked ourselves, do you actually need PT symmetry to achieve that? And the answer is no. You can actually also get such an effect for structures, dielectric structures that don't have a special symmetry. Let's, for example, consider a dielectric index distribution like the one shown here. And we were asking the question, is there a way that you can add a gain-loss distribution to this structure, such as to make it unidirectionally invisible? Let's first of all have a look at what happens if you send a wave onto the structure that doesn't have gain and loss. Well, in that case, there will be back reflection, only part of the wave will be transmitted, and there will be lots of interference going on in the middle. And the question that we asked is, which kind of gain and loss distribution should we add such that actually no such variations occur and you will get full transmission? The solution to this problem is something that I presented in this seminar last time. It's those so-called constant intensity waves. I will briefly review them here. So let's assume you describe your scattering problem with a simple Helmholtz equation. So we are talking about stationary waves. Psi is something like the electric field. And this is the Helmholtz equation that describes the distribution of the electric field at the wave number k and in the presence of a dielectric function that varies in space. And if we now demand that we get a solution that has a constant intensity, so the absolute value of psi is flat in space. Well, and we make this ansatz that we have sort of a plane wave, but not with a uniform evolution of the phase, but with a sort of WKB form where we have an integral over an unknown function W that describes the phase evolution. Then if we make such an ansatz, we can conclude that such solutions exist, provided that the dielectric function has this specific form, where again this unknown function W, which is real by the way, otherwise you wouldn't get just a phase, but also sort of attenuation and amplification. If this function W is real, then the dielectric function is given through this function W. And this form has been identified earlier by a Japanese scientist called Wadati. That's why many people call this the Wadati potential. Actually, late Wadati, he introduced this potential to create actually PT symmetric potentials. And several people have been working with this. I also mentioned here the group of Rodney McConaughey. And we were the first ones actually to show in this work that the Wadati potential gives rise to those constant intensity wave solutions that have an intensity that is constant all over space, although you have a non-uniform dielectric function here. And of course, what makes this happen is that this Wadati form of this dielectric function doesn't just have a real part, but it also has gain and loss. And this gain and loss comes from the derivative of this function W, and it shows up here. Let me just show you a simple example. For example, if we go back to this potential from before, and we add the corresponding gain and loss distribution to it, then it looks like this. So gain and loss are distributed in space according to this form. And if we have this form here and inject the wave through a potential that both has a real epsilon and imaginary epsilon, then we will get a wave that doesn't have any intensity variations anymore and is perfectly transmitted.
There's a question from Philip. Philip?
Yes, it's just a very quick comment. If you can go back one slide. Yes, I think what's interesting about this formula is that even when epsilon is complex, W is real.
Yes, but in this case, we sort of start with a W, yes, and from the real W, we obtain a complex epsilon. Yeah, so that's not right. All complex epsilons can be written in this form.
Oh, no, absolutely. But the ones that can have still enable W to be real. That's what I find remarkable.
Yeah, yeah. Mm-hmm.
Well, thank you.
And I will show, by the way, to make sort of a cliffhanger here in my presentation, that this W doesn't come from somewhere, but it has a very special meaning. And what this meaning is, will have connection to transformation optics. But this is sort of something I will only show in like 15 minutes. So please hang on. Okay, so I showed you that with such a W, we can get such a potential. And in this special case, because the W function is left-right symmetric, we indeed get the potential that is PT symmetric. So if you look, sort of gain and loss have a PT symmetric distribution. But if the function W is not left-right symmetric, but it's an arbitrary flux function, like here, so we have a disordered medium that doesn't have any symmetry, then even for such complicated media, provided that they satisfy this Wadati form, you will be able to, write down this potential and show that it's unidirectionally invisible from the left, not from the right. And to show this explicitly, I have prepared this animation where a pulse is launched in a disordered medium without any gain and loss. Then in the constant intensity Wadati potential with the gain and loss, and then a uniform medium that doesn't scatter at all. And what you will see is that in the medium that is disordered, of course, the wave will enter, it will be partially back reflected and scattered. But in the constant intensity wave potential, the pulse will propagate exactly as in the uniform medium. So which makes it clear that this pulse propagates through this medium as if through a uniform medium, then you will not be able to distinguish between those two, making this potential here, in spite of the disorder, completely invisible when you look at it from the right side and you just see the pulse. Then, well, you cannot tell whether it came from this potential or it came from this potential. Okay, so
Stefan, yeah. This is unless you can measure the phase as well. No, if you measure the phase, you know if it's
no.
You'd have to measure W. Yes.
No. So the point is that if I look, I can show this explicitly. So if the integral over W, which is the phase, is exactly the same as when I go from beginning to the end of the medium in free space, where the phase is just NKL, then even the phase will be the same.
Okay.
So it means that there are sort of constant intensity waves that do not correspond to this uniform medium, but if I tune sort of the W correctly, then even the phase can be made such that there is it's the same as in this uniform medium, and then even the phase is the same, and you cannot distinguish between the two.
Yeah. May I make another brief comment?
Sure.
Yeah. So obviously, to the extent the Helmholtz equation is like the Schrödinger equation, in this case, the one-dimensional one. If you allow the amplitude of psi to vary as well, namely making W not real but complex, of course you have an infinite family of the so-called reflectionless potentials, like the special Poschel-Teller. But then there are, on one hand, you have this infinite family of potentials. On the other hand, in your case, for a particular form of matter, if you tune correctly the epsilon, then for a particular wave you will have it reflectionless for that medium that you engineer somehow.
Yeah, not only reflectionless but full transmission. So everything that you send in comes out. But I perfectly agree that I can also sort of modify the W to take complex values, and then, for example, I can get potentials that are equivalent to those that people use when they talk about the perfectly matched layer. So you send in something to a potential and it's perfectly sucked up. So this would be sort of a potential that corresponds to W that then sort of fully absorbs but is still reflectionless. And this is what people want in numerics, for instance, when they want to send a wave somewhere, because they don't want to simulate all of space, but just a finite extent, and then they want every outgoing wave to be perfectly absorbed.
Okay, thank you.
Absolutely, yeah.
Stefan, Uwe is asking a question concerning this special form of this coupling with this potential. It very much reminds about supersymmetry. Is that
a very good point? Yes, it's very strongly connected to supersymmetry also. Yeah.
Okay. Thank you.
So we have, and this is a comment I want to make here publicly. There is a very strong connection to supersymmetry, because sort of also there you have a quadratic and the form and the derivative there, and we have already sort of investigated this, but we have never published anything on it because we have never sort of managed to go deeper there what the fundamental connection is, or whether this is sort of a meaningful connection that also sort of has a sort of a deep physics connection or not. This is something I don't know, but there is definitely a connection. Yeah?
Okay, thank you very much for the comment.
Okay, sure. Okay, this whole construction can also be, by the way, generalized to 2D. This is what we have shown recently in this Optica paper. So here is a Gaussian laser beam that enters a complex refractive index landscape and gets scattered. But if to this complex, to this real refractive index landscape, we also add an imaginary part following the Vardati form, but now in 2D, then this Gaussian laser beam will enter this potential and propagate through this complex landscape as if it was sort of a uniform medium. Yeah, and this is something that was recently also realized in an experiment in the Rostock group in Germany, in the group of Alex Samait. So Alex and his team, they're specialized in time multiplexing photonics. So what does that mean? Well, they send a pulse into a system of two coupled fiber loops. One is longer, one is shorter. And then here in the middle, there's a beam splitter. And in each of the loops, they have a phase shifter, PM, and an acousto-optical modulator, that is the gain and the loss part. And then you can show that when you send in those pulses and they're split each and every time, this is equivalent to the propagation in a network where you send in a pulse and it can go to the left or to the right. It gets gain and loss, and then again left to the right. And sort of in this network, you sort of realize a discrete photonic walk, and this sort of can be mapped to a discretized Helmholtz equation. So in those kind of systems, you can implement gain and loss and study discrete photonics with gain and loss. And indeed, what they showed in the experiment is that if you launch a Gaussian laser beam, this is actually the Gaussian here at the beginning in a non-Hermitian lattice, where the gain here is matched to the index profile according to the constant intensity wave concept, then this Gaussian laser beam will propagate sort of for a considerable time without any distortions, apart from experimental imperfections, through this medium. If you don't add the gain and loss, then you see that the same Gaussian laser beam breaks up pretty quickly, and you get some filaments, and it doesn't propagate so nicely. So this is the first optical realization of this concept of constant intensity waves in a lattice. It was published just very recently in Science Advances. Okay, so now comes the question that I've been asking myself actually since we started working on those constant intensity waves, and I've been asking myself, why does this actually work so well? Why is it that sort of those constant intensity wave solutions, they are so stable, even if you have a disordered medium? How can it actually be that those solutions exist at all? Isn't there a fundamental connection to, so where does this W come from? And what's the fundamental physics about it? To solve this question, we teamed up with Ulf Leonhardt from the Weizmann Institute, who has been visiting us now for the last 3 summers here in Vienna. And Ulf is an expert in so-called transformation optics. I will explain briefly what transformation optics is. But when talking to Ulf, we understood that there is a deep connection between those constant intensity waves and a transformation of space. So let's just look at the 1D example. Let's assume you have a 1D space parameterized by the coordinate x prime. On this space, you again have a Helmholtz equation, and the refractive index in this space is uniform. And let's assume that you're looking at a plane wave that propagates from the left to the right and has this simple form. Now, let's assume that this space is sort of flexible. It's like a rubber band, and you can sort of distort it. For example, I can compress this rubber band here, I can stretch it here, and I can do whatever I want, as long as the length of the rubber band in total from left to the right stays the same. Yeah, let's assume that I can do that. Then I can introduce, and that's the basic concept of transformation optics. And in this field, people call sort of the space of x prime, they call this the virtual space. And the distorted space would then be called the real or physical space x. That, of course, due to this stretching and compressing, has sort of a functional relationship with the original space x prime. And now you can ask you can make the following statement, that in real space, sort of the equation from up there must have the same form. So the electric fields must be the same here and here at the same wave number k0. If you make a transformation from the virtual space to the real space, The only thing that changes actually due to this transformation is actually the dielectric constant n of x. Yeah, and so if you do the transformation and you have to calculate the Jacobian, you have to sort of transform the derivatives from virtual space to real space, and you do everything correctly, then you will find that the dielectric function in this transformed space has the following form. It involves two terms, and both of the terms involve sort of a derivative of the virtual space coordinate x prime with respect to the physical space coordinate x. Yeah? But if you look very carefully, you will see that this derivative shows up here with a square, and here it shows up with a second derivative. So if I call dx x prime my function w, then this here will exactly be the Vedati form that I was introducing in the first part of my talk. Was there a question?
Yeah, Stefan. So I want to get it right. The electric field is scalar with respect to this general coordinate transformation. That's what I get from the formula.
So here I was just trying to present the most simple example, 1D scalar. But
no, I'm saying E prime of x prime is E of x, no? In your
yes, exactly. Yeah.
So it's a scalar. It's a scalar.
It's a scalar. Yeah.
So okay, so this is not a Einsteinian sort of general coordinate transformation. It's just some ad hoc or whatever you do in this transformational optics. I shouldn't think in terms of general relativity or special relativity.
You're exactly raising the right point. So Ulf Leonhard, actually, when he sort of invented this transformation optics idea with conformal mappings, he was actually working before on general relativity, and he was asking himself the question, what happens actually if I make a coordinate transformation like in general relativity now with corresponding distortions in space, and how does this affect the fields that I'm working with? And this is exactly where this is coming from.
Okay, but in general relativity, the electric field is a tensor of rank 2. It's not a scalar.
This is for a scalar field.
This is for a scalar field.
That's what I was asking.
Yeah, so maybe to give you the answer on the next slide, I show it that in general, transformation optics is for transforming sort of the Maxwell equations from virtual space to a physical space. And of course, there you have sort of very complex coordinate transformations. And what you can show is that the form of those equations is the same for epsilon and the mu and epsilon prime and mu prime when they are related by the Jacobian transformation matrix.
Okay.
And what Ulf showed, for instance, was that if you do very special transformations that are called conformal transformations, and a conformal transformation is a transformation that preserves the angles. So here a 90-degree angle will also be a 90-degree angle here. Then you will get materials. So the epsilon and mu in the physical space will then be isotropic materials. If you don't have this conformality, then you will get anisotropic materials. Yeah. So there are certain depending on the transformation that you do between this virtual and the physical space, you will get other types of materials. And of course, what you want in the end in transformation optics is you want to transform your space in such a way that, for example, you blow up a point to a whole sphere by making a corresponding transformation. Because in the sphere, in physical space, you would then be able to hide something or cloak it by the object that would then result from the coordinate transformation around the space that is inaccessible in this physical space. And that's the idea of cloaking an object that comes from those transformations. The problematic
Philip,
part, yeah.
Want to add to this, or is this hand just
Yes. I believe that what you're doing is simply saying that the Maxwell equations in empty space with a constant refractive index are conformal invariant, and therefore you can make conformal transformations as you've done. But what bothers me is the boundary conditions also have to transform. And I think if the boundary conditions transform, then you've got a tautology, then you have no new information. It's only if you use a different set of boundary conditions for the transformed electric and magnetic fields that you can claim a different physical outcome.
Well, for example, let's assume the following situation. I have a point in space that has a certain boundary condition, let's say Dirichlet-Neumann boundary condition. Then, of course, if I scatter at a point, I will just scatter at this point. But if I blow up the point with the same boundary condition and I have a Dirichlet boundary condition then at the sphere, then this sphere would, of course, without cloaking, scatter much more. But if sort of as a result of the transformation, I have a sphere and I have sort of a cloak around it, then this large object with the cloak around it will only scatter as much as the point that I had originally in my virtual space.
But Dirichlet and Neumann are conformal invariant boundary conditions, so that's okay.
Yeah. Mm-hmm.
Well, even if the boundary conditions are conformal invariant, there's no physics in the conformal transformation. Changing the conformal phase of the electromagnetic field doesn't give you new physics.
Well, in the end, but that's the statement that I'm trying to make here is that it's the same physics, but in a transformed space. But if you blow up a point to a sphere, it means that everything that is then within the sphere cannot be accessed from the outside, and that's what you want in transformation optics.
Oh no, I take back a little what I said. If you want to conformally transform the Maxwell equations, you have to conformally transform the metric as well. And I think what you've done is not transform the metric. If you were to, in other words, if you were to transform the metric as well, then I believe you have a tautology.
Well, in the end, what I'm doing is I'm making a coordinate transformation, and I'm asking myself, how can I sort of get the same type of equation, but everything then now being sort of put into this effective refractive index distribution, which of course in 3D will be sort of in principle a tensorial distribution and whatnot. But this will give me a solution to the question, how would I have to sort of construct a dielectric distribution, or doesn't have to be dielectric. In the more general case, it's also can be sort of with non-dielectric and anisotropic materials, but they will then sort of have a mapping between sort of my virtual space and my physical space.
Okay.
Okay.
Stefan, there's another question.
Yes.
This equation that you showed here, is it probably it's closely related to the Schwarzian derivative and its relation to conformal structures and projective space underlying it?
That may very well be, but I'm not an expert in this.
Okay.
Definitely, there's a lot of math behind this that comes from general relativity, and also sort of the coordinate transformations that are being done. You can also, for example, write them with complex coordinates, and then sort of this is all related to complex analysis and all the theorems that have already been derived there.
Yeah, sure. Okay. Thank
you. Okay.
Yeah,
okay. So I'm trying to show you sort of how such a transformation was typically done. So let's, for example, a standard transformation that is called a Shukovsky map. Here, people considered a line. So consider the light green line. In this light green line, by a conformal transformation that would respect the angles, and this transformation would look like that, would then transform into a circle. And this circle in the Shukovsky map that would map this line to a circle, this would be the region that is inaccessible. So if you have a wave coming in from infinity, then this wave would be guided around this object. But if, and now comes the interesting story, if you do such a conformal transformation, then you will end up with a dielectric distribution that goes to 0 here at those 2 points. And this is, of course, very hard to realize because those epsilon near 0 materials are sort of they have very sharp resonances, and they're in general very hard to realize. So what can we now contribute with our story? Well, if we now sort of take this transformation that we introduced before, but we don't say this is a conformal transformation, but we also allow non-conformal parts, then we would get such a transformation. So such a dielectric index function plus many other terms here that I don't show because they would fill 3 lines. Now, the interesting thing is that such non-conformal transformations lead to very complicated solutions, and this is why in most cases they have not been considered. However, these additional terms, they are bound to the specific solution that you have in virtual space. And if I now say my solution virtual space is just a plane wave incoming from the left, then it turns out that those additional terms all vanish, and you will just end up with this simple expression. And in this simple expression, we can now, with this simple expression, we can now make a non-conformal modified Joukowsky map that maps this dark green line to a circle. This is shown here. And if we look at the dielectric distribution that we get as a result, then we see that we get a real index, refractive index in the front and in the back of the circle, but also we will get loss and gain. There will be a lossy part in front and a gain part in the back. So we naturally end up with a parity time symmetric dielectric profile as a result of this coordinate transformation. And because of the fact that we are not bound to conformal transformations, we are more flexible, and then we can design our system in such a way that the real part of the refractive index will always be larger than 1. So we don't have this problem of having to work with materials that have a refractive index close to 0. But instead, we end up with a non-Hermitian material, so a non-Hermitian dielectric. I will show you now the solution. So here is the uncloaked object. So this is sort of a cylinder, and we send a plane wave from the left, and it will of course scatter a lot. But if around the cylinder we put a dielectric distribution from here that contains gain and loss, you will see that the plane wave coming in from the left propagates across this region without any scattering. Of course, the price that we have to pay is that the solution only works for the correct solution in virtual space, which was a plane wave incoming from the left. If, for example, I take a plane wave and tilt it a little bit, then the more I tilt it, the more scattering I will get. So in this sense, sort of, we gain more flexibility by having a non-conformal transformation, and we get sort of non-Hermitian dielectrics as a result. But the price we have to pay is that the regime for which this works is more restricted in the sense that we cannot go into arbitrary angles, which is also clear because if I came from the back, then I wouldn't see first loss and then gain, but then I would see first gain and then loss, and then of course this wouldn't work. So in this sense, this is also a unidirectional invisible cloak that only works for a specific plane wave incoming from the left. Okay, so this was published this year, and it also made it to the PAL cover. However, at PAL they decided not to show the cloaked part, but actually the uncloaked part, which is, from my perspective, it's not the interesting one, but okay. Okay, so I've saved the last interesting part for the last slide. So, which puts this concept, which makes this concept interesting in my eyes. I already said these epsilon near 0 materials, they have very sharp resonances, but this type of cloak should be a broadband. So as long as in the gain-loss distribution there are no sharp resonances, this should work not only for a specific frequency, but also for neighboring frequencies. This means that if, for example, I send a pulse that is a plane wave and a Gaussian combined onto this object, and I would usually get scattering, then by putting the cloak here, I would be able to even send the pulse at this region and get no scattering at all. Yeah, so to summarize this part of my talk, by studying non-conformal transformations, we naturally end up with constant intensity waves. So the solutions that we get are the constant intensity wave solutions. So in other words, the constant intensity waves work so well because they are the plane waves from free space transformed into a deformed physical space. And this is why sort of the fundamental origin or explanation for why the constant intensity waves work so well is because they are just plane waves in a deformed space, and the dielectric function that enables them is just coming from the Jacobian of this transformation. And this can be generalized from 1D to 2D, and even works for pulses impinging on the structure. Okay, so how am I doing with time? Can I still show a few slides or?
Sure.
Yeah, okay.
You definitely have 20 minutes left.
Okay, very good. Then in the second part of my talk, I would present some recent work that actually has an interesting connection to something that you may have observed in nature. So if you look into the eyes of animals that hunt at night, you will see that their eyes tend to light up if you shine at them with a flash lamp. Why is that actually? Have you ever asked yourself the question why that is? It's actually a non-Hermitian effect. And the reason why animals that hunt at night have this effect, but as humans we don't have it, is because those animals that hunt at night, they have to cope with the fact that during the night there's not much light available. So they use this effect to see better, or to use the dim light that is available at night to see better. And why does this mean that they have such a reflecting eyes? It turns out that the eyes of those animals, they work in a similar way as ours, of course. The light comes in, there's the retina, but what those animals have and we don't is that behind the retina, they have a so-called tapetum lucidum, which is a light carpet. And here you actually see an image of this from a cow. It's like a mirror that is placed right behind the retina. And those animals have this because in this way, the light that passes through the retina doesn't just pass through once, but it passes through twice, on the way to the mirror and on the way back. So in this sense, the retina that absorbs light only very weakly passes through the retina twice, and those animals can use the light sort of more efficiently than humans can, because in our case, the light passes just through once. So in that sense, what those animals are good at is they use very dim light in a very efficient way by letting it pass through a weakly absorbing layer. And the question I'm going to ask now is, can you actually do better? Is there a way to improve the absorption in a very weak layer? Let's assume you want sort of the light to get even better absorbed than by passing it, letting it pass through twice. And of course, you may have guessed already that a good solution may be to actually put another mirror in front, because in that case, you don't let the light just pass through twice, but actually multiple times. But if you look at this image more carefully, you will realize it's actually not so easy. Why? Well, if the mirror here in front, that is here partially reflecting, if it reflects too much, then the light here will not even enter this cavity, and you will get no absorption at all. If the front mirror reflects too little, then you're back to the situation before where there's no mirror there as we had in the first place.
So you want one-way mirror. The second one should be one-way.
Yes, I want a one-way mirror, but I don't want to use complicated materials that may actually realize this. But you're exactly right. I want a one-way mirror. How could I do that? Well, the answer is I can use a concept that was recently discussed. It's called a coherent perfect absorber.
Oh.
Okay, so the idea is to time reverse a laser. This was a concept introduced by my postdoc supervisor, Doug Stone at Yale, together with his team, and Wei Cao, Yideng Chong, Li Ge, and they realized that if you have a laser that consists of a gain material and two mirrors, and it emits light to the left and right, Then when you time reverse the laser, it means that gain has to turn to loss and the outgoing light becomes incoming light. Yeah? So this would be, imagine a laser that shines and you record it in a camera and then you let the movie run backwards, then you would get a movie of light coming in and be perfectly absorbed. Yeah? But if you think about it carefully, it's not so trivial because the light comes in and you would think there's a mirror, it already gets reflected. How can this be perfectly absorbed? Well, the answer is this reflected part gets interferometrically cancelled out by the light coming from the other direction, and they just interferometrically destroy each other, such that even though there's a mirror, this light does not get reflected by the mirror because of the multiple interference that is exactly tuned in such a way that no reflection occurs. So, okay, how would we use that in the present context? Well, if I go back to this thing here, then I'm not sure if I can use the concept of a time reversed laser because, you know, I want light from all different angles to be perfectly absorbed. But if I time reverse such a laser, this only works for light that goes out in one specific direction. If I would then sort of take this laser and send in light from different directions, it wouldn't be perfectly absorbed. So this solution so far works only for a single mode, only for the mode that exactly corresponds to the outgoing laser mode, but in time reversed, which is here a mode that comes in perpendicular to the mirror surface. And the question is, how could we sort of design a structure that would be flexible in the sense that light can come in from all different directions? And the answer is, again, you have to time reverse a laser. But what kind of a laser would you have to time reverse? The answer is you would have to time reverse a laser that also doesn't just emit in one mode, but in different modes. And what would be a laser that emits in many different modes? Well, such a laser exists, and it's called a 4F cavity laser or a degenerate cavity laser. It has been studied a lot, for example, in the group of Neil Davidson at the Weizmann Institute. This is a very special laser. It consists of two mirrors and two lenses in a so-called telescopic arrangement. So any image that you have here in this telescopic arrangement will be imaged back to where it is. So in other words, each beam, not only the straight ones, but even the tilted ones, would be perfectly mapped back to the entrance mirror. And in that way, each of those light rays is a laser on its own. So this is then a laser where thousands of laser modes laser at the same time. And if I time reverse such a laser, well, okay, I would have to again replace the gain by the loss, and the outgoing light is replaced by the incoming light. This is shown here. And then I would have a cavity with a weakly absorbing element inside that would perfectly absorb, under the right conditions, beams coming in from any directions. So let's have a more specific look. How would this work? So this is shown on the next slide. Let's, for example, take a tilted laser beam that comes from the top left. It impinges on the partially transparent mirror, and part of the beam would be reflected here at the mirror already at the entrance. This is shown here. Part of the beam would enter. Sorry, something happened with my mouse. And because of this special construction with the lenses, this transmitted beam first goes through this absorbing layer, then to the lenses, it's back reflected, it goes again to the lenses, and then because of the self-imaging capacity of this cavity, it comes back exactly to the position where it enters. And because it's so finely tuned, this beam, maybe I should use the laser pointer, this beam here cancels exactly that beam, such that no beam is reflected. So in other words, I have a mirror that would usually reflect, but because of the construction behind it, it doesn't reflect under the right conditions. And this condition also works for any incoming beam. So even if the beam doesn't come from the top, but it comes from the side, the lenses always guide back the beam to where it enters, and there's always a perfect cancellation happening. Yeah. And such kind of cavities is something that Ori Katz at the Hebrew University in Jerusalem was working on. And actually, he heard a talk of my student at the Ein Gedi workshop at the Dead Sea 2 years ago. And in the coffee break, he came to me and said, shouldn't we use such a degenerate cavity and time reverse it? Wouldn't that sort of yield actually a coherent perfect absorber for many modes? And I was immediately excited about it. We collaborated, and he built up the setup in his lab in Jerusalem. This is an image of it. And the experiment looks like this. He creates sort of a complex light field to demonstrate that this is an absorber that works for many different modes. And on this spatial light modulator, he creates a light field that is very complex. It's a speckle pattern, but in the form of a yin-yang symbol. And of course, this speckle pattern contains input light from many different directions. So it's a very complex light field that usually in such a coherent perfect absorber would never be perfectly absorbed. But in this cavity with 2 lenses and a weak absorber here, he would measure which part of the light that he sends in, so that's the incoming light, would be back reflected, and then he would measure this on the camera. Yeah, and what he observed is that if the interference condition is not met, then he would see the same image that he sent in, just with very, very little attenuation. But if the 2 mirrors are tuned exactly to the resonance condition between the 2 mirrors, then almost nothing would come back. And tune this, he had a piezo stage on the last mirror, and he could show that the absorption is really perfect here, then almost no absorption, perfect here, and so on. So he demonstrated in the lab that this concept really works, even for very complex light fields. Yes, Philip, you have a question?
Yes. If you're sending energy in and it's not coming back, where does it go?
It goes to the weak absorber.
So, I mean, eventually you'll burn it out.
Well, the laser is not strong enough that it will burn the weak absorber, but of course the absorber will heat up and it will radiate in a Planckian spectrum, the heat to infinity. But sort of, thank you for the question. The interesting concept here is that, of course, if I put a strong absorber there, like a black substance, then I would trivially get a strong absorber. But this is a weak absorber that would usually only absorb 15% of the light that passes through. And because of this construction, we can make this weak absorber be an almost perfect absorber with more than 95% absorption. So this means that this effect of coherent perfect absorption can be used to make a substance that would usually only absorb very weakly into a super absorber.
I see.
So let's assume, for example, you have a detector, or like the retina in the eyes of the cat. This detector wants to detect light, but at a single pass, it only absorbs 15%. But you want to sort of be more efficient in terms of the detection. Well, if you put this detector then in this 4F cavity, then you can make it very strongly absorbing because of this interference effect. Okay?
Yeah, I think what you said about the thermal distribution, it seems in the camera, you're going to see a black body.
Sorry, in the camera, what?
In the camera, you'll see a black body spectrum.
Yes, but the camera is tuned to the wavelength where the laser comes in.
If it were tuned appropriately.
Yes, but I would assume that sort of there's probably more black body radiation from the experimentalist standing next to the experiment than the weak absorber here. Which, yeah, okay. Okay, I will also show you a movie where we show sort of how the reflection as a function of the mirror position, how this looks. And you see the yin-yang symbol. Then if the mirror is tuned correctly, you get it perfectly absorbed. Then it comes back, and again it's perfectly absorbed, comes back. So it's really sort of a highly tunable system where you can switch between strong absorption, weak absorption, and just by shifting the end mirror a little bit. So then we had the idea to study whether this is a fact that is also robust and it works for extremely complicated light fields like speckle patterns that even move in time. So let's assume you have a laser, you shine it through the atmosphere, and in the atmosphere, sort of the field gets distorted. This is, by the way, a big problem for astronomers when they look at stars, because the starlight gets distorted in the atmosphere. So in order to test whether even for such dynamically changing speckle patterns, this concept works, they actually used something like a hair dryer, put it under the laser beam, and sort of created those turbulent airflows. And what they found is that the whole thing works just as well, because sort of the interferometric absorption condition is the same, and the absorption happens so fast that compared to the time scale in which the airflow moves, this is still extremely fast. So they showed that even sort of a field that comes out of a multimode fiber that they shake, and then they put a sort of a turbulent atmosphere, the whole thing still works just as well. So we think that with this, we have really found sort of a solution for how to absorb even complicated speckle patterns coming in at different angles in a highly efficient way, which removes one of the central obstacles of this concept of coherent perfect absorption that so far only worked for a single incoming mode. Okay, with this I come to the conclusion. So to summarize part one, I started out with constant intensity waves in non-Hermitian media. I showed you that they have recently been observed in discrete lattices in the group of Alex Samad in Rostock. And we found, I think, a very nice explanation for why those constant intensity waves work so well. This is because they are linked to non-conformal coordinate transformations. And with this, we could build a broadband dielectric cloak based on gain and loss. So here are the corresponding publications that both came out this year. In the second part, I was talking about a coherent perfect absorber that would trick a weakly absorbing layer to be a perfect absorber. This works even for very complex beams. It is a comparatively simple design, and it's even robust with respect to time-dependent modulations. And the paper about this just came out a few weeks ago in Science. Good. I shouldn't forget to mention all the people who were involved in this. On the constant intensity waves, we have a long-standing collaboration with Kostas Makris, and recently also with Ulf Leonhardt from the Weizmann Institute. My hero on this project is Ivo Kresic, who really sort of did the code calculations and sort of guided this project from conception to a publication. He's a postdoc from Croatia currently in the group. Andre and Philip were involved in the constant intensity wave story a while ago. So Andrea Steinfurt and Alex Samad are the main guys from Rostock who implemented this in the experiment in Rostock. And here is the team from the Hebrew University, Evgeny Slobodkin and Gil Weinberg, the graduate students of Ori Katz, who is the PI of the complex imaging group at the Hebrew University, and Helmut Hörner and Kevin Pichner are the graduate students that worked on this project very efficiently in our group. Okay, with this, I've come to the end, and thank you very much for your attention.
Thank you very much, Stefan.
Thank you, Stefan.
Thank you.
Questions, comments, or more questions, more comments? Yeah, Philip.
I have a very general question. We commonly write the Maxwell equations and we replace epsilon 0 by epsilon of x and use it, which is exactly how you've been proceeding. But if we try to derive the Maxwell equations from an action, and we put a variable refractive index in the action, then when we take the variation, we're going to pick up derivatives of the refractive index.
Mm-hmm.
And so could it be that your result is working because even though you have a variable w and you have an epsilon, which is w squared minus I w prime, that somehow epsilon prime is small?
No, I'm not relying on this assumption.
Okay, well then it seems that you're using an equation which is not valid. because I mean, if the theory of
Well, maybe I haven't made one point very clear.
Yeah.
If we write down this non-conformal mapping, then in general you will get many additional terms, and maybe if you allow me, I could even show those terms. Let me check if I can show this quickly. So here, yeah. So here is the supplemental material of our paper, and you start out with a Helmholtz equation here on top. That's the electric field in 2D. And then we write it in a more compact form using complex coordinates, where z is x plus iy. And then you make those derivatives, and then you make a coordinate transformation that looks like this. And this is not something that we invented, but this is sort of standard transformation optics procedure. And usually in this transformation, you assume that the transformation does only depend on z and not at the same time on z star, the complex conjugate of z. And this is the requirement for a conformal transformation. Here, however, we loosen this up and we say we have a non-conformal transformation. And as a result, we get a dielectric index distribution in real space that has this complicated form distributed over those two lines. This is why I didn't show them in my talk. But what you see here is that the terms that are left out, they also depend not only on the transformation, but also on the solution E in virtual space that you started from. So this is a sort of a solution that really depends on what kind of wave or what kind of electric field distribution you have in the virtual space to begin with. And what we show is that if you have a plane wave in the virtual space, then many of those terms sort of cancel out, and you will end up with a very simple form, which is actually shown here, which is exactly the form that describes constant intensity wave solutions. Yeah. But if, for example, I would have another solution in my virtual space, then I will get additional complicated terms, and then this would be very complicated. Yeah, and this is probably the reason why many people have stopped at this point, because it looks like this will lead to nowhere if you do it. But this is very technical matter. Maybe it's good to just have a look at our paper, which is that one. As the PL from this year, and the supplemental material where all the details are given, and also the connection to the constant intensity waves.
Okay.
Yeah, okay.
Julio.
Stefan, I have a question for you. A question about the Vedati potential in 2D.
Yes.
The Vedati potential involves, the Vedati potential includes a derivative. It's actually includes it linearly. So how do you generalize the Vedati potential to 2 dimensions?
Well, this is what I just showed on this slide. I will go back to the supplemental material of this paper. So the Vedati potential in 2D looks like that. Yeah. Where here is the Vedati potential as a function of this parameter, or of this function W, here written as theta, and here it's written as a function of the coordinate transformation between x and x prime. Yeah, but it sort of looks very similar, only that you don't have the W being a function in 1D, but you have a function theta that is a 2-dimensional function, and it involves here the Nabla operator and the Laplacian, but in principle it nicely generalizes to 2D.
This is called the Canal equation, I think, in multi-dimensions.
Without the I term.
Yes, exactly. So,
Yeah, but in one dimension, the Vadati potential involves the derivative of the first order only.
yeah, so here the W is the nabla of that. So that's the W squared, and this is the W prime.
Aha.
Yeah, so here I just wrote it in the following sense that the theta is the integral of W. This is why you have an additional derivative there.
I see now. Okay, great. Thank you.
But it nicely generalizes, actually. Yeah.
Yeah, okay, great. Thank you. Thanks very much.
Julio is next.
Okay, thank you. Stefan, I wanted to make a comment about this the conformal Joukowsky transformation.
Yeah.
Because this Joukowsky transformation is used in airfoil design, and there you use it you map there is the profile of a wing or the airplane wing to a cylinder, and this is the relation with using conformal transformation. And then in that case, you introduce a vortex, which is just that the circle is rotating. And in this way, you obtain the lift that keeps the plane.
I think this is also for the problem for which Joukowsky introduced this transformation, right?
Yeah, I suppose that. So I wonder if this description using the vortex, it could be useful in your case. And I also wonder if this non-Hermitian conformal transformation, Joukowsky transformation, could be useful in airfoil design. This is
well, first of all, the first question I would ask here is if I sort of transform what I did here to other domains of physics, what does the imaginary part here, what would that correspond to? Because I'm sure that if you talk about airflow or so, or you solve a Navier-Stokes equation, then it's probably not so obvious what gain and loss in this context would mean. But maybe there are processes where gain and loss can play a role. But to be honest, the Joukowsky map for us was just one first example for which we wanted to demonstrate that this can be done. But I'm pretty sure that there are many more exciting potentials and transformations, where interesting non-Hermitian potentials would come out. But, we haven't tested them yet. We just took one potential that is known to the community in transformation optics to illustrate the concept. But there are, this doesn't mean that this is the best one. Or, for example, Ivor is currently working on other potentials where the values of gain and loss that are required are minimized, where sort of you can get cloaking with emission dielectrics with only very small values of gain and loss, and there are transformations for which this requirement is satisfied in a much more efficient way. So, the whole parameter space of 2D is available for improving this. This was really just the first example.
Oh, thank you.
Francisco.
Yes, thank you, Stefan. So in the case of reflectionless potential and the Wadati potential you mentioned, this is kind of clear, at least for me, the relation with supersymmetry. There is a connection, but actually there is an entire family, a huge family of reflectionless potential. Will we not satisfy the Wadati kind of equation, but all of them, they will be connected via supersymmetry. And there is all the reflectionless potential in that sense, all of them, they are constructed using supersymmetry. So do you know how this kind of impacts here, or this might?
No, I don't know, but I think it's an exciting thing to investigate. I think honestly that the connection to supersymmetry and transformation optics, and I have the feeling that there's still lots to discover, actually. And maybe I should also mention that I remember reading in a paper by Simon Horsley that those constant intensity waves have another interesting connection to the so-called Jacques-Rebbe modes from high energy physics.
Yes. Yeah.
I think there are many connections, and I'm sure that in all of those fields where those solutions have already been studied, people have investigated different aspects, and it would be really interesting to take the knowledge from that fields and connect it to optics and non-Hermitian physics. So I think this is really many questions are unexplored here.
So may I have a comment and question?
Sure.
Yes. Okay. So first of all, you showed the equation for the Laplacian under your transformation coordinate transformation. That can you show it again? Del by del z bar equals blah blah blah.
Okay, you mean from this supplemental material?
Yeah.
Okay. Mm-hmm.
So I think that's what confused me, and also to some extent Phil in the beginning. But now I see this Laplacian that you calculate is not the it's not scalar with respect to this coordinate transformation. The scalar Laplacian is 1 over square root of the metric d mu. Current is g mu nu, d nu, square root of g, etc., etc. So this doesn't satisfy that equation, and therefore it's not a scalar with respect to your coordinate transformation, and therefore you shouldn't have, for example, an analog of the equivalence principle in general relativity, so that you could make every wave, let's say, into constant amplitude wave or something like that. So probably
this is not something I was claiming, right?
but then you okay, but
what I was saying is
then you change the wave, then you have to change the material, so to speak, right?
Yeah. So what I'm saying is that if I have a certain solution in my homogeneous virtual space and I transform to another space, then sort of in this real space, the transformation can be put into a transformation of the corresponding n squared in our case, but in 3D and vectorial waves, it will be the epsilon and the mu. But the solutions in those two spaces will be equivalent, only that sort of in one case you have a homogeneous space, and in the other physical space you have sort of a complicated material distribution that depends exactly on the transformation that you have. And in our case, in addition, it doesn't just depend on the transformation, but it also depends on the original solution, which in our case was the plane wave solution that we started out from in virtual space.
Okay, I guess what I'm saying, not every complex n squared could be satisfy this special property that you require, and therefore.
No, I agree. Yes. Mm-hmm.
So
yes.
that's what I meant, that you don't have an analog of
okay. I think I understand it.
Principle because Laplacian is not the scalar Laplacian. Another question is concerns the coherent perfect absorption. Yeah. Your last part.
Yeah.
If I think mathematically, if I have to explain this to a mathematician, then you are telling me that I should go to a system which scatters waves and it might have a complicated S matrix, and in that system, S matrix might not be unitary, it might be subunitary because you have absorption. And then in this subunitary S matrix, you somehow engineer the zeros. The S matrix it doesn't have only poles. Yeah, it also has zeros.
Yeah.
And engineer the zeros such that they will be quite dense around the real axis in the case wave, something like that.
Exactly right. So, but the difference is that typically if you have a complex medium, then if the medium doesn't have gain and loss, you will have poles in the lower half of the complex plane, and you will have zeros in the upper half of the complex plane.
Yes,
If you
yes.
then add absorption, you will be able to drag the zeros down, and when they hit
Yes,
they
yes.
hit the real axis, then when injecting an eigenstate that corresponds to this zero eigenvalue of the scattering matrix, then this specific individual mode will be perfectly absorbed.
So this
Yeah.
special laser in the Hebrew University is quite robust. It has many.
And this special laser doesn't just bring the zeros down, but it actually brings 1,000 zeros down together to the same location on the real axis. So it's a massively degenerate absorber. And because you have a hugely degenerate subspace that you create at the absorber, it means that any input field can be represented in the subspace, and in that sense, every mode that you then send in will be perfectly absorbed because you have a huge degeneracy there.
And this huge degeneracy assures the so to speak robustness of this
Exactly.
option. Yeah. Oh, okay. Thank you.
So you don't just have an individual zero that gives you perfect absorption for the corresponding mode, but you have a whole subspace of zeros on the real axis that spans sort of the whole over the whole numerical aperture of your cavity, and no matter what you send in at the specific frequency, it will be perfectly absorbed. Yeah.
I understand. Thank you. Thank you. Very, very nice.
Thanks for the question.
More questions, comments? Well, if not, let's thank Stefan again for this very nice talk.
Thank you.
Stefan.
Thank you, Stefan.
I applaud also the organizers for organizing a perfect meeting, and I thank you really for setting this up. And thanks everybody for coming and for giving me the opportunity to present my work.
Thank you.
Good.
Thank you.
Thank you.
May we ask you the slides, Stefan?
Sure. Yes. Yes.
Thank you.
I will remove the videos because it's 200 megabytes.
Okay.
So,
okay.
are there many parties in Vienna this time after the announcement earlier this week?
Well, there was, of course, a celebration at the University of Vienna. And I know people who have been there, but since I'm at the technical university, you know, I was actually preparing my talk.
For you.
Okay, good.
Okay.
Thank you.
Bye-bye.
Bye-bye.
Okay, bye everybody. We have
Bye-bye.
to next week. For a while, we do it weekly. Yeah.
Oh.
Because we had such a long break, so let's start a bit intensely, no?
Okay. Okay.
Okay. Bye-bye.
Bye-bye.
Bye-bye, everybody.
Bye.
Bye-bye.
Bye.
Bye-bye.